Hello everyone, welcome to the channel. Today we are diving into a new concept of mathematics which is complex numbers and also a powerful theorem which can help us work with them which is Moivre's theorem. So let's start with the basics and a quick introduction to complex numbers. What exactly a complex number is? Well, it's a number that extends the concept of real numbers. We usually represent it in a form of a plus bi or a minus bi. Here, A is what we call as the real part of the complex number and B is the imaginary part. The crucial element here is I, which is defined with the property I square equals to minus 1. The I is the imaginary unit and it's what allows us to work with the square roots of negative number. Let's talk about a couple of important operations that we can perform on complex numbers. The conjugate and the modulus. First, the conjugate of a complex number can be represented as z bar equals to a minus bi, and also the modulus, which is known as magnitude of complex number, as mod of z equals to under root a square plus b square. While we can express polar form as a complex number in terms of magnitude r and its angle theta with respect to positive axis in the complex plane, which would look like z equals to r cos I or theta plus I sin I or theta. As we have discussed here, r is the modulus, r equals to mod of z, and theta is the angle which can be found by using the formula tan inverse y by a, y by x or b by a. Then we have Euler's formula which gives us exponential form of the complex numbers. This connects the complex number to exponential function which equals z equals to r e raised to I theta or I we can say it as. Now let's move towards the De Moivre's theorem, which is the main concept of this video. This is a cornerstone for working with powers and roots of complex numbers. De Moivre's theorem states that for any integer n, cos theta plus I sin theta raised to n is equals to cos n theta plus I sin n theta. It essentially tells us that when you raise your complex number in the polar form to the power, you raise the modulus to that power and multiply the angle by that power. This simplifies the calculation tremendously. So, why complex numbers and De Moivre's theorem are important? Because they have a wide range of real-world application across various fields. The fields are listed below. Now we'll see them one by one. As of electrical engineering, complex numbers are fundamental for representing alternating currents, voltages, and currents, often phasors. They are also crucial in impedance calculations, which is essential for designing and analyzing the circuits. Also for control system, it control systems complex numbers are used for stability analysis, particularly through the use of complex pools. Signal processing. Many signal processing techniques such as Fourier transforms rely on heavily complex exponentials to break down signals into their constituent frequencies. Now we'll move further to the next point, which is solving an equation by using De Moivre's theorem. So our first step in solving any equation regarding to it must be finding the mod of z and argent of z, which is theta, by the formula tan inverse y by x. So first step we can start by writing this equation and representing it as z, and then considering this 1 as a and 3 as b, and then we can put it in the formula as a square plus b square, and then we can get the value of mod of z. And for getting the theta, which is essential in the formula of De Moivre's theorem as r raised to n cos theta plus I sin theta, we can find this theta by this formula tan inverse y by z. So we can consider it again as x and y, and by substituting the value, we get the total value of 2 pi by 3. And then we can apply the De Moivre's theorem formula, which is r raised to n cos theta plus I sin theta, as we have to substitute the value of theta here, and then we have to add the value 2k pi into the theta, addition it to the theta. So we can add it, and then the next step is writing the r value of r outside it by writing their exponential, and then we can simplify whatever we have got into the simplest form. This is our final equations, and then we can calculate the roots for different values of k. For example, k equals to 0, 1, 2, 3 until the last value which we have in our exponential. This is determined by the exponential which here we have, which is in this example we have raised to 4. So we can calculate it 4 times, which is 0, 1, 2 and 3. By the similar calculations we can get the values of all the roots as shown here. So De Moivre's theorem makes this process much straightforward than trying to solve it algebraically in the a plus ib form. Thank you for watching. I hope this explanation of complex number and De Moivre's theorem was clear and helpful.